You guys, any questions on anything?
We're going to go through PP again, the calculation of the units and the chains.
Yeah. B. Comment on the problems C. Oh, the problems with his, so I listed a bunch of problems, right? Let's see, the chains can. So the first thing he's calculating so it's the program's calculating the Kuhn, the persistence length, which is like half the Kuhn unit, whatever. But so and it's doing with that. All right, so there's a bunch of problems, right? So I list some here. So so the way he makes it like a super dilute solution, like micromoles. And then he pours that over. So he has a mica, so he cleaves a mica crystal, and then he treats the surface with a silane coupling agent that's got an amine functional group sticking up that's positively charged. And he pours, I think he kind of pours his solution over that. So it's tether, what they call that, a tethering of the chains, which is known to change the conformation. But for instance, so let's see. I put a thing up here. There's a lot you don't have to write all this down for the answer to this thing, but basically there's a lot that you could do. So I copied, someone emailed me and I kind of trimmed their things and I put down some stuff. So this is here where it says comments. I just put that in just now, actually. So, oops, I didn't want to do that. But so anyway, I want to go back to that. There. All right. So if you just go into Google, you just say Google Scholar and you can get papers. Then you can just put in like tethered polymer chain structure change or something like that. So I just did that and I got like 1,000 papers, where they talk about when a polymer tethers to a surface, the structure of it changes. Especially if it's most of them are like end tethering, so you have like a kind of a hairy growth of polymers off the surface. And then that'll depend a lot on the density of the polymers that are going in, so they can squeeze each other, and then they can actually become like rigid rods due to the packing together on the surface, making like a hairy surface. And then they can also, if they're less dense on the surface, they can make like a collapsed ball, so they can like smush down. It's like, in this case, they're not doing end linking, they're doing this total linking, right? So there's not that many people that look at that because that's like a total devastating effect, right? In other words, normally you have a surface and you want to put polymers on it, you might want to have them, this is kind of like a brush. But it's a 2D surface. It kind of would be like a brush. And then you can make it so that they're lower densities. You have then they smush down into kind of pancakes. Or they could be trees. Right. So so they could be kind of tree-like. So anyway, they're going to change. So people have studied this ad nauseum in simulations and in experiment. There's literally like probably 5,000 papers in the subject, and this is called end linking. And then what he's doing though, he has the polyelectrolyte and it's tethering like all the way along. So that's like end linking times a billion or something, right? So it's kind of like ramping up end linking, which is already known to distort the chains. So it's a little crazy to say you're going to look at the conformation of something that it's going to change the conformation when you tether it. And he's using the cations. The group he's using is NH2, so it's like NH. Anyway, ends up positively charged in the surface, right? So then he's got this anion, the carboxylic groups, and he's looking at how how the conformation of that changes when he adds like Mg+2 to it, so cation. So he's got a cationic surface. So he's studying this and then he's putting it onto a cationic surface, which it doesn't make any sense. Like that's exactly the feature that he's trying to measure, is what he's using to tether the thing to the surface. And tethering it to the surface changes the conformation. So it's kind of like, the more you look at it, the more you can see like there's some kind of craziness involved in this. And no, it's surprising it didn't kind of come out in review, I guess. But anyway, and this thing, I can't, it's pretty small. Oh, wait, this is the problem with your homeworks too. Oh, on the homeworks, you can only click 2 times in the Concord, you can't, so sometimes you paste something and keep in mind that you can't see it. Like if it's a small thing you paste in, I can only zoom it twice on the Concord. Then I can download it and zoom more, but anyway, I listed a bunch of things here, whatever. This is just off the top of my head, so you might find some more things. What else is it? So yeah, I mean, he's calculating. So if you look at the micrographs, you can't see with your looking at the micrograph that there's any change at all, right? So that's a big problem. Like you should be able to, if you're going to measure something, you really want to see it first and then quantify it with the app that you're using, and then you want to verify that the app, what you see is kind of what the app says, except you have an error bar. That's the advantage of using the app other than just using a ruler with your hand, right? So he uses the app and he doesn't report the error bar. That's kind of a signature that something's dicey about the whole thing. Like if you do a measurement, so you report a number like you're 6 feet tall, then like that number is kind of useless if you don't say plus or minus an inch. If it's plus or minus a foot, whether you're on the basketball team or not is going to make a big difference, So the error in the measurement is actually sometimes more important than the measurement itself, because it tells you, can you measure it or not? Like yes or no. Like if it's plus or minus 6 feet, then basically we have no idea what your height is, right? So the error can, at least if you know the error and that I can measure the error, or I can believe what you're saying about height. So anyway, you always have to put an error bar when you put a number in. I used to teach the characterization class, and I'd take like 1 point off for every number you put that didn't have an error bar in it. And like people would get like zero, like -100 for the reports, or -1,000 or something. It'd be a lot of numbers. And eventually they learned to put in the error bars. Then like 3 or 4 years later, they do a PhD dissertation and they show a table and it's like no error bars on any of the numbers they're reporting. So it's like things go in one ear and out the other. So that's partly why I gave up teaching that class, because it's like useless, People thought they were learning stuff, but anyway, error bar is kind of a useful thing to think about whenever you report a number. He doesn't report any here. That's a big problem with this whole thing. Anyway, one impact. I don't know, I say some things in here, but basically, I thought he had a big list for B, but I think it's mostly that the technique he's using seems to distort the chains, and he doesn't even bother to, like, all right, what he could do is he could do 2 measurements, one with his pour the thing over the surface and one like dynamic light scattering, right? One real analytic measurement that's known to work. Then does he get the same number with the 2? And he doesn't do that either. So you kind of cross-check it as possible. I didn't check the references. So in the references, they might do that. Like he cites one paper, it's the original one that did this method. They might do this cross-check thing in it. So you might feel comfortable doing it, but it seems a little fishy to me. So that's kind of B. Let's see. So, oh, here's the B. I did list a bunch of things here. Oh, I listed it I. That's cations, bonding chains to the surface. There's no perceptible or obvious difference in the micrographs. It's not sufficient sample size. So when you're doing say you do a dynamic light scattering measurement to get it, well, inside, even if it's 1,000, whatever it is, 0.01%, yeah.
They just did one sample for each one of those.
Yeah, I think they popped one
Operations and-
picture that's, I mean, it takes a while to get an AFM.
So okay, they only did one.
That's all they report. I mean, I have to assume they only did one, yeah. Right, so it's kind of like, all right, and then no error bars. So I mean, it's kind of like, Yeah, when you look at it, yeah, it's a little bit, starts to get wishy-washy. First glance, it's pretty good. Like it's nice, it's click, and it follows the theory and everything agrees. But then you start looking at it and it's, well, this method seems a little fishy. And like, how many of these micrographs did you take? And it's like, nowhere does it say anything except what they show, just one. Yeah, and then it's like nowhere near enough, right? I mean, two dynamic light scattering, if it's so dilute, I mean, you're getting like at least millions, probably maybe billions of chains that you're averaging over, right? So that's like a decent number. Anyway, so this is how you like review papers. Like it's kind of a good exercise. Like you get sent a paper and you have to read it, then you figure out kind of what's going on. And then the more you read it, the worse it gets. You only want to read it once, or review proposals and things, I mean, at some point you'll do this. Or just review someone's working for you and you have to look at what they did, or one of your peers or whatever. So you have to kind of be critical. It's good if you can do it in a helpful way and be nice about it, because I mean, but basically people can take it wrong, or anyway, people are difficult to deal with, but in terms of science, then you have to have this kind of cut and dry thing. Like it's either, and if there's problems, you have to point them out. That's kind of the legitimate thing to do, unless they're paying you under the table or something, So there are reasons why you might not, I don't know. Anyway, there's not sufficient sample size, and we know this chain ends. So he doesn't, all right. So if you take his final LP number times 2 to get the Kuhn length, then look at the micrograph and see how many there would be in a chain. You end up with like 50, I guess I got, or you might get less than that. But anyway, it's nowhere near enough to ignore chain end effects. He's got a program that gives him basically what the simulations give. So it's kind of analyzing. So he could get the persistence as a function of chain length, but he didn't do that. And then he ignores the chain end effect, which is something we talked about. Figure 4 should have error bars. That's it, I guess. And this tethering thing, he should mention at least that there's like so many papers on tethering of chains of surfaces and how it changes the conformation. So, I mean, I just put that in, but then I don't want to spend too much time on this, but anyway, this is up there to buy, like, so yeah.
For C, is it saying as the ionic strength increases, the persistence length will decrease or increase?
Decrease.
Decrease. Okay.
Yeah. Yeah, so it screens the charge. So the charging makes it linear, and then if you get rid of the charge, it'll go down to a coil. Yeah. Yeah, the picture is actually in this. Oh, one of the last slides here. So this is our polyelectrolyte. Is that up there? Yeah, that's the polyelectrolyte, the blue. Then if you get rid of the charges, it turns into this grayish black one. So it's a significant change in the persistence and chain size. Right. So we almost have a rigid rod with the charges on it, and then it's going to go to that thing when you get rid of the charges. So it's a big reduction in it. And they say that it would go directly 1 over the concentration of the counterions, according to the OSF theory. And that yeah, people had a problem like, I don't know. Anyway, I don't really want to go through the whole thing, but deriving the OSF, this 1072 thing, Dobrin, and that's why I put that in there, is that you can use other sources, but basically this thing. So this is the idea, like it could be straight, or if it bent, then the charges come closer. So there's a change in the energy of the system. There's Q squared over R is the energy of a Coulombic interaction, and R changes when you bend it. So then you can get a delta U. That delta U is related to theta. That's the basic idea, just that you bend it and they get closer. And then that's the basis of this. And then it isn't exactly to follow it. I mean, you should maybe show this picture or hand draw it, or then just say like they're closer. So that there's an energy difference. That energy difference, they can calculate how the persistence length changes relative to KT. Now it's energy delta U and then KT. How do they match up? At higher temperature, you overcome this delta U thing, and I guess they bend easier. And at lower temperature, you can't overcome that delta U, so they stay straight. There's a temperature dependence, and so basically this gives a temperature dependence to the electrostatic. And that gives you this 1 over the Debye length squared, which ends up being 1 over the concentration. Debye length is 1 over the square root of the concentration, and then the square of that's 1 over the concentration, which is exactly what he gets in the paper. So he gets that in the paper. He plots versus the Kuhn length versus the persistence length. So he sees exactly that, so it's, all right, it's only 3 points with no error bars, but he's plotting log of persistence versus, this is the Debye screening length. 1 over kappa is the screening length. And then log plot, the slope is the power of the screening length, which is 2 here. Should give you, and that's proportional to 1 over concentration to 1 power, which is the prediction of the OSF. So that's like perfect, but no error bars. So if the error bars are this big, he has no dependence. He only has 3 points. Like 2 points would give a line. He has the third one that kind of makes you feel more comfortable. But what would make you even more comfortable is to see the error bars, which he should have, so he doesn't show those. I mean, you could kind of guess what the error bars are from the 3 points that you have, but if it was 2 points and no error bar, it's meaningless. So you're putting all your weight on like the other point. How much you can believe that, you don't know. Anyway, it's always good to, when someone's showing a dependence, and cover up one of the points and see if you change your mind. That's really important to do, because basically you need to do that. That's the best way to see if you really believe it. Because the lines can be misleading, they guide your thought. So you cover up a point, maybe the most vital point, and then you still believe it. So anyway, that thing. Then there's this, then people asked some questions, and the more I got into it, the more I thought, and I thought, I really believed like he had a pretty good story, like these series, but then he talks about, and he says that the different counter ions, this should be lambda, but he says for the different counter ions, their affinity changes, and they're in the order of affinity, which you kind of take at face value, like he must know what he's talking about. But then you think, like, what is affinity? It doesn't have a definition. He doesn't define it. So you could look at something called the for anions, to say electronegativity, and this kind of electropositivity for cations, but it's really called the ionization energy. And you can look at it in the periodic table, and you find out, and that would be like how much it would attract an anion. I guess that would be the affinity. All right, so if you do that, it isn't the order he says. That's like a big problem. There's no feature of these cations that follows that trend. He just says affinity, and he doesn't define it. So that's kind of weird. I mean, you didn't have to put this in your answer, but basically this is kind of when I started looking at it. And then I talked about the balloon thing, but I never said, like, the balloon thing relies on that the ions are bigger or smaller, right? So the biggest one would have the the smallest lambda, because it would be closer to the straight persistence, because it would be stretching it out by putting larger balloons on. So and you assume that he has like figured this out, like what's the size of a cation, so you can get that just by Googling the size of the cations. There's a periodic table with the sizes, and it doesn't work out. Like calcium, potassium's the largest, magnesium's the smallest. So they get smaller going right, and they get larger going down. So basically, it isn't the order that he says. It's messed up. In fact, it's the opposite order, and one of them, the middle one, goes to the end. So it's nothing to do with the order that he observes. So that's both of his series of lambdas don't seem to have any way to link them back to reality. So anyway, it's kind of weird, because I just took it like, yeah, that's right. That sounds pretty good. That could work. And then you go and look, and there's like, no, there's no evidence for that. Like, that isn't how these things work. So anyway, I was misled by that, but anyway, it's there. So you don't need to put that in, but basically I just thought I'd put those up. Anything else on this stuff or, yeah?
Wrong, or like this theory doesn't necessarily
I-
align with the value.
I think that you could put that if you want, but you don't have to, but whatever you got's fine. Don't rewrite it unless you know. But basically, I just thought I'd show that because I was kind of surprised. Both of the series, there isn't any evidence of what he said, you know. Like what he said, he just spins it off like affinity. He talks about kind of thing. And he doesn't give any numbers, you know. And then you just go like, oh yeah, that makes sense. He must have looked up the numbers. But when you look up the numbers, no, and all you have to do is Google like ion whatever, and it's right there in Google, you know. It isn't like you have to spend an hour searching for something. So
Order that MG was the biggest.
yeah, MG's the smallest.
Yeah.
Yeah, right. MG is the smallest. I know, I was pretty surprised about that. When you think of magnesium, you're kind of thinking big. In my mind, it's big, you know, but it isn't. It's really small. And it gets smaller as you go across. So it's pretty weird. Like, anyway, that's how it is. And that's why, yeah, that's why the paper is convincing, because obviously magnesium +2 has to be bigger, you know, but it isn't. It's the smallest. Yeah, it's kind of surprising. Anyway, that's some points that I had on that. Any other stuff on that? Yeah. Yeah, he didn't. I mean, I think you'll find yourself doing this too at some point, you know? Like I go, like I said, you know, so in this class, like people were like getting zeros on lab reports. And then finally they got the idea to put in the error bar. Then 3 years later, they give a number like in nanometers, like 1. Oh, sorry. I mean, they'll have a table with I just mentioned this because I want to reinforce the idea. They have a table and it's in nanometers and it's 1.00532987. And there's 50 of these numbers on this table, right? Written that way with no error bar, right? So this is an angstrom. This is like a picometer. That's something that doesn't have a name, you know, it's so small. It'd be like subatomic particle, right? And they're measuring it with a TEM. Like you can't see subatomic particles with that. So, I mean, you need some atomic accelerator or something to see it, right? So anyway, so it's a point like people just in one ear and out the other. Like, so whenever you report a number, so you have to calculate the error. Like even just like you guess what the error is. Like I can't measure an angstrom with this machine. I can measure a nanometer, so it's plus or minus a nanometer. And then at that case, then you figure out how many numbers you report. You don't report beyond what you can believe, right? So otherwise you're lying to people, right? Or you're lying to yourself. Like you'll say, oh, that one was that number and this one was like this number. So obviously that one's larger, you know, but your resolution is 1 nanometer. So there's no difference. You can't perceive it. There might be a difference, but you can't perceive it, you know? So anyway, I don't want to dwell on that, but I just did. But anyway, that's what gets me when I see that, you know, in student, you know, when they do their PhD defense, and it's like in 5 years and they still that thing. So anyway, so let's see. So yeah, so I wanted to finish this guy off, this section. All right, so what we got, so we're done with that thing. Then there's some other, so we're talking about size scales like much smaller than the chain on a local size scale. I already mentioned like Kuhn length, persistence length. And then I mentioned a little bit tube diameter, and maybe I'll talk about it later on more. So that's what got to do with this reptation theory, that the chains are gonna follow like a path, a primitive path, they call it, that's made up of the entangled chains around it. So there's a lot of simulation papers. So there's a Kuhn length of the chains, and then the tube diameter, and then the packing length we already talked about. So I'll mention that at the end here. But basically the tube diameter, I just want to mention that it exists. But we already seen it a couple of times, I think. But so this reptation model, the idea that the chains are moving by a kind of like a train through here so that the motion goes with the molecular weight. The more cars you put on, the harder it is to pull the train through. And then when it gets to be an entangled melt, they have to move through these kind of weasel holes that squiggle through where the entanglements are. And then the reason that people know that exists is this dynamic neutron scattering measurement. So they measure the intensity. So Q is the scattering vector. So you're going to have, let's see. So we'll talk about this later on a little bit, but basically, so you have, so we have that thing I showed you before, that you have a beam coming in with a single wavelength going out with another wavelength, and there's these kind of points where the two could interact, and they're separated by distance. This distance kind of d, and q is 2 pi over that size. And as you change the angle, so basically 2 pi, 2 pi over that size is q over d, and q's also 4 pi over lambda sine of the scattering angle, which is that one over 2, and your diffraction angle is kind of where these things are going. So like that's theta, that's theta, that's theta, and that'll be 2 theta. So in scattering, you call that whole thing theta. In XRD, you call that 2 theta, because half theta would be the direction those points are in. So you get some size scale that you're looking at that's related to this Q number. And then it's, since sine of a small angle is the sine of a small angle, the theta small is the angle. So this is Q is just basically the angle reduced by the wavelength. So it's kind of just the angle for at small angles. Okay, so you have that gives a size scale. So if you think about the chain, and it's in this network of other chains, so, and it can move freely kind of below this size scale, the tube diameter, because it's got walls around it, but within that tube, it can wiggle around all at once, right? So it's kind of freely moving as much as it wants. And then as you get to larger Q, then it's stuck because it can't move past the walls. So if you can probe as a function of Q, so at low Q, which is large size, because it's 1 over size, then you expect stuck. And then at high Q, so at low Q and high Q, you expect free, which would be this kind of Rouse, what they call Rouse scaling, which means that the viscosity goes with the molecular weight. So it's kind of like add train cars onto the one more car on, adds more, slows it down more. So basically, you expect to see a transition in Q of this kind of motion. So you fix your detector here, then you measure as a function of time. And as you measure a function of time, the intensity is going to, because these things are moving, it's going to be fluctuating about an average intensity. This is time. So it's fluctuating around. So you can do a correlation function on that as a function of delta t between those two. So if delta t is 0, they're correlated. So the correlation function is 1. Then as delta t goes to longer and longer, it's random fluctuation, so it goes to 0. So you expect to see this kind of exponential decay, t over tau. That's a relaxation time for whatever q, if this is at a fixed q, whatever q you're at. So you have I, q for size, and then t for time. And you expect that thing to look like that, like a decay in time, e minus t over tau. This is time, this is your kind of the intensity that you're looking at. So that's what, so in short, and sorry that's like quick, but that's kind of what you're looking at here is an exponential decay. So if you're at really high Q, so really small size, it decays down to almost 0. Right, that's a reptation. Like in fact, that's a Rouse. A Rouse would be look like that. It would go to actually 0. As you go to smaller, smaller Q, boom, all of a sudden there's a wall. So all of a sudden it doesn't change at all. It's flat. So that's how you can measure. So 2 pi over that Q value is the tube diameter. So that's how it was determined that actually existed. Before they did that measurement, the Jens and Edwards predicted that would happen. Then they did the measurement, and bingo, there it was. So then there's actually an experimental way you can measure this tube diameter. Then verify that there actually is this thing that happens. a cheaper way to do it. So this is a nuclear reactor you need to build first and on it. So this is kind of total like maybe $200 or $300 million experiment if you think about it. Cheaper way to do it is to take a DNA and put it in a network of other DNAs, then put a tether on it that's like a charge group you can pull down electrophoretically to the bottom, then watch the chain, it'll just follow its own path through. So that's a cheap way to do it. This is a maybe $1,000 measurement, to do that, because you need fluorescent microscope and things. So, and you can measure actually the time of that chain moving through a real chain. Even cheaper way, the $5 way, is to just get a computer simulation and just do it and say, oh yeah, there's a tube there, So supercomputer, which they give away free in Ohio for some length of time, and then just let it cook for a little while, and you can make the network and let it equilibrate and find out there's a tube and the chain moves through a tube. And then you can map out all those primitive, so the tube path is called the primitive path. You can map out all those in space. I mean, the actual simulation looks like that. If you just find the primitive paths, then they look like that through the thing. So it's pretty well verified. So if you use that tube model, you find out that this is another measurement. So anyway, this is just another measurement of the neutron scattering to watch the breadth of a peak decay with the time type thing. Anyway, so and the other measurements are so I'll talk a little bit more about the dynamic things. This is a pretty simple one done by this Jacob Klein, who's like early Polymer guy. I think he's in Israel, like Technion or something. So just make a layer, one layer polymer and another polymer. Some are tagged, uses just an IR microscope. Then he looks how the interface changes with time. And then if you follow the fixed second law and integrate it, you get this kind of function for how that curve would be. And the dotted line is that thing, and the data is that. The argument and this thing's a diffusion coefficient. So you can plot that versus molecular weight. And if that reptation theory works, that should go with molecular weight squared, and that's exactly what he got. So that's like a seminal paper on showing that the tube exists. I forget what year, probably in the 1980s, something like that. So anyway, so the tube thing is pretty well verified by a few different cheap and expensive measurements. And the tube diameter is the thing you can look at. The problem with the tube model, it can predict that so you have that if you plot the log of the viscosity versus log of the molecular weight, so you have this power 1 region, that's Rouse. Thing. Add another car, you get one more viscosity. Then all of a sudden, when you get entanglements, it shoots up to 3.4 slope. So viscosity goes from molecular weight to the 3.4 power. And then if you use this reptation model, you find out viscosity equals molecular weight to the 3. It was missing the 0.4. For that reason, they wanted to get this 0.4. So they said that, well, yeah, it's in a tube that's made up of other chains. And the chain within the tube is, they call it relaxing, meaning it's moving through the tube by random motion, by Rouse motion along the tube. At the same time, all the other chains are in their own tubes, and all those tubes are relaxing too. So because you have constraint release, then you get this, you can predict the 3.4 from that. So they've kind of gotten that molecular weight dependence by looking at combination of reptation through a tube, and the tubes aren't fixed. The tubes relax with time. Tube renewal, they call it. Constraint release, tube renewal. I mean, it's gone. So this is like a lot of times they'll have like branch chains like this. So you have like, in order for this thing to move through a melt of itself, each of these branches has to relax through reptation. Then the whole thing has to move out. So it's gotten to be pretty elaborate, like the kind of whole complicated things you can talk about. That's important to polyethylene, actually, that business about branching. Anyway, so I just wanted to mention briefly the tube diameter, because it's on the same size scale. And then this packing length is the thing I wanted to kind of go through today, which is short too. So so anyway, so we talked about the packing length in terms of that you can predict the plateau modulus versus this packing length will give a perfect match for all polymers, right? So that's where you get the plateau modulus, the storage modulus goes up and then reaches a point where you have a time where the entanglements are stuck because you go into higher and higher frequency, shorter times. So the entanglements can't relax anymore. Then it acts as if it's a cross-link rubber. It's got a single modulus, and that goes with 1 over ME according to the thing we did, the 3 KT over ML squared. So ME is the molecular weight of the chains there to get the spring constant, right? So it's 1 over ME. Anyway, the packing length can give that to you too. And we can just use this packing length. So I just thought it was kind of interesting, like the origin of the packing length has nothing to do with that. Like, and this guy, Tom Whitten, who was at University of Chicago, so he was at University of Michigan, and then they wouldn't give him tenure. He's like one of the smartest guys in the world, probably. He's retired now, but basically he did a lot of seminal stuff in polymers and in other fields too. But and Milner's at NIST. Don't know Wang. I don't know who that is, but anyway, so this block copolymer paper was the origin of the I think it's like, I don't know, it's a long time ago, but block copolymers. So block copolymer, it's the origin of this packing length idea, like what didn't exist before that, and then after that, people kind of hooked onto it, So you have like an A group. So you polymerize. So if you do anionic polymerization, you can polymerize like polystyrene, and it's got a anion on the end instead of a free radical, and it polymerizes. And then when you run out of styrene monomer, it just stops, and you still have an active anion, right? So then you can put in like butadiene. Let's see, 1, 2, 3, 4. There's 2 double bonds in it, so like that. So butadiene, so it'll go in and polymerize. So butadiene can also anionic polymerize, so it can go in there. So you can have like aromatic chain, and then this unsaturated rubber chain, right? So that's SBR rubber, like tire rubber, right? So, and it can be a die block, and it still have an anion when it's done, so you can just add in more styrene. You can just keep polymerizing. There's no termination step in it. And you can terminate it when you want, but there's no termination in the reaction. So you can make as many, you can make SB, SB, SB. You can just keep doing that if you want, right? So you can make as many, and you can make these blocks any size you want. So anyway, so that can be used to make tires. So tires are going to be like styrene domains that are like kind of cross-link sites, and butadiene that are, and then so you have a rubber that's kind of made up of. So that's a thermoplastic elastomer. You can melt the styrene at 110, and then you can extrude it, and then when it cools, it makes a rubber. Or in tires, they do that, and then they just cross-link this with sulfur at the double bonds. So it's kind of a permanent, it doesn't melt at 110, right? So, all right, you can also use that to template making electronic components. See if you can get a, all right, so basically these kind of systems, they found out early on that they'll form these kind of structures. So if you get, so FA here is like how much the A component, which would be like styrene. So say the red component is A. Well, if it's a small amount of butadiene and a large amount of styrene, then the butadiene will cluster together into a sphere, and then you have styrene as a matrix. So you have spheres. On the other end, if you have mostly styrene and not much butadiene, the styrene forms a matrix and butadiene forms the spheres. So you can get either one that you want by changing the block lengths of the two, right? And then the middle, so if they're length, you get a lamellar structure. It's like stacked up lamellae. And then here you get cylinders, and in between there's this kind of interpenetrating network that can form, called a gyroid structure, double diamond structure. So anyway, so this is a whole, like there's many people doing work with block copolymers, right? So the issue back in the 70s or 80s, I guess, was how do you predict like what the size of these domains are going to be? Okay, so there's 2 issues with this. Yeah. It's so compatibilizer means if you want to, say you want to swell the styrene domain, the red domain, to make it larger, you just throw in linear styrene. So it can swell that domain up. I'm not sure what it means as compatibilizer. That's not really right here. You could put in I'm not sure what compatibilizer means there. It shouldn't be there, sorry. Basically, the idea of a homopolymer is you can change the size by adding in another polymer, the same polymer, just to make that domain swelled more. So there's a variety of tricks people use for these things. Right, but the main idea is you get like sphere, cylinder, lamellae, cylinder, sphere. It's the same as for micelles, you get almost the same thing. So it's kind of like nano micelles. So because the chain, so typically a polymer chain's like 10 nanometer, the coil size, so you're kind of looking at 10 nanometer resolution of some kind of regular structure. I mean, you can do things like, if one of them, so you can etch out parts of this if you want and end up with just the other's phase, or you can infiltrate one of the phases. If it's water soluble, you can put in a ceramic precursor in it, then burn the polymer and just have that structure on a ceramic. So templating. So you can do a bunch of things with these. So it's kind of, there's a lot of research in block copolymer, right? But the idea is like physics, like how do you predict what the size is? Like we can make a microelectronic circuit with this, like transistors. You need to know like what size you're going to get, and you want it to be as sharp a resolution as you can get. So to get a sharp resolution, you make the compatibility between the two blocks poor, right? As poor as you can get. Then they want to phase separate more and more. Then how is that going to impact your size resolution on this? Yeah, I mean, usually you're looking for nano size out of these, like monodispersed nano size, perfectly aligned over macroscopic dimensions. That's the desire, right? So to get that, you have a high incompatibility between the two. And then you mess around with the molecular weight of the two blocks or the total chain to change the size, right? So question is like, how can you write an equation for that? Yeah.
Previous slide, you mentioned the simulation that here we see. I want to know what kind of simulation are we doing?
This is just molecular dynamics. Can what? Lamps. You'd use lamps or Hamid blue. It's simple to do, I think, at this point. Like you can just Google the lamps code and just plug it in and it would do it for you. And you could change the interaction, put different polymers in. It would be really simple to do. It originally hard, now it's very simple. Now it's just written for you already. Did you have something? It's just a local thing. So it's just got to do with the entanglements and the chain and like the chain structure. So it doesn't have to do with branching. It shouldn't have to do with branching. The branching should affect the plateau modulus, but not the packing lengths. I don't know how that pans out. I think that's just for linear chains, that plot. So the plateau modulus would be affected, but the packing length isn't. That's kind of a good point, but to think about it. So, all right, anything else or? All right, so anyway, so you want to know what this size is. So you're going to do this energy balance. You want to get an expression for the free energy of the setup, Will-Meller setup. So you have equal molecular weight between the two. And the interfacial energy is going to be this enthalpic term, this is like the energy of interaction per unit of the chain per kT. I'll talk about this actually in the next section, but basically this is enthalpic interaction for each mer unit in the chain, and it's measured in per kT per mer of A and B. Right, so this is an average interaction energy, and then per mer unit. So you have to say, well, chi times kT will give you the enthalpy because this is per kT, then times the number of the MER units in this interfacial region where the A and B, that's the only place where A and B see each other. So that's like the thickness of the interfacial region, then the area of the interfacial region. So this is where the packing length comes in. So the area is like the lateral size of a chain, which was never used before, right? So Witten kind of put this area in here, just stuffed it in. And this is the volume of one MER unit of the chain, BC. But occupied volume of a unit segment of the polymer chain, just one unit. So that gives you the interfacial energy. And then opposing, so that's going to make it want to separate. And then opposing that is that the chains have to stretch out to, and that's our spring constant again, the 3 kT. So the energy, the modulus is 3 kT over NL squared, but the energy is 3 kT over 2 NL squared, so 3/2, and then the R squared is the energy. So that's just our energy that we had from the beginning, right? The comparison of the Boltzmann with the random walk thing. So so you can see like that thing's useful, use it everywhere. So you know the energy of the chain, there it is. Then so with that, you can rearrange this thing to include let's see. So you say, let's see, 3 kT, so DAB, say the occupied volume is the distance DAB of the chain times the cross-sectional area again. So you can rearrange that DAB is NAB times VC is the occupied volume of the chain, and then divide by the area, you get DAB. So you can plug that in here and get this equation that replaces, and then R squared is NL squared. So you can plug that in, and you get this expression just for the chain elongation, just by substituting in this guy that came from that, and this thing, which is our NL squared thing. You get that thing. Then you add those two together, so that's got the thing that's making them make the microdomains, then the thing that's making them not make the microdomains, which is the stretching. You have the free energy, so you want to find the minimum in that. So you find an equilibrium condition, take the derivative, set to 0, and then you can solve for the area. So this packing thing, the area is what you solve for. And once you solve for that, because DAB depends on the area, and the other things, you know the molecular weight and you know the volume of a unit, then you can calculate what DAB is. What's the length of this thing? In other words, the size of your domains from the minimum of that thing. So it spits out, and then that's been verified by scattering, basically, or microscopy, right? So it's kind of a simple thing. You have the stretching and the interaction, right? So the problem is you want to have to get very sharp features for something like making microelectronics with it. You want to have a big chi to make it phase separate sharply, and then the big chi messes with your size here. So somehow there's a competition between the interaction and the desired size that you get. They aren't independent of each other. So that's one of the problems with using this for microelectronics. But so anyway, from that, all right, so you got that area idea, which is the packing length essentially. So that area in this paper, he defines like this intrinsic elasticity, this A parameter that's related to the A, and basically eventually in the same paper, he gets to the term packing length that he comes out with. So this idea of intrinsic elasticity that relates back to the plateau modulus is in that paper. And then the packing length term is in that paper too. It has nothing to do with plateau modulus, which is the main application of it afterwards. Yeah, so it's kind of funny, like by messing around with this kind of thing, ends up with a thing that does this, like does that thing, like gives you the plateau modulus. So it's kind of an interesting little weasel thing, so anyway, so that business, packing length is pretty relatively popular, this is up to 2023. I couldn't get this plot anymore on Web of Science, but basically there's some papers, there's like thousands of papers on packing length now, something like that. So the main ones are this Loshi guy who's retired now from Exxon Central Research, and Fetters was at Cornell now. He was also at Exxon, and then Gracely's a Princeton guy. So they're like the main guys dealing with this. basically it's a polymer rheology guy. Anyway, so the next part is about chain scaling, like so that's kind of like short range or local things that happen. And the next part is about how the chains accommodate like excluded volume, right? So kind of a separate thing. Any questions on anything or?
If put you down there,
Yeah,
right, so if using Q,
yeah,
Q there isn't the chat.
no, that's a good question. The Q is the scattering thing, it's the size thing. It's good that you brought that up. So this is all, let's see. This is time here. This is versus time, and each one of these is a different Q in inverse angstrom. So that's the scattering size. Like you come in with that and you go out with that, and it's the size between where the things where they overlap each other. So as you change angle, that size goes from lambda to infinity. If you get to very small angles, you get to infinity. That overlap becomes infinite. Right. So it's an inverse size. That's the size from the scattering. So you change the angle that you measure at, and then you sit at that angle and wait. This is nanoseconds. So you kind of wait a second. So you have a detector that's really fast. I think that's nanoseconds, right? So you watch that decay is pretty fast, but basically you can measure it. There's a way to measure it somehow. I don't know how, but right. So you're kind of looking at this time decay. You're expecting it to go to zero if it's totally free. If it's doing route like that, then the confinement you can see as you go to lower sizes, there's a size dependence to the confinement. You reach some large enough size, it can't move because it's stuck in a tube. It's hitting the other chains. Right. So, yeah.
Is Rouse dynamics at a particular Q, or is it like variable based off of conditions?
Well, I mean, you get Rouse dynamics when you have low molecular weight, like in a oligomer melt, like wax. This shows Rouse dynamics. Then you get up to like 10,000 grams per mole, and then you start seeing this reptation stuff.
Okay.
So the chains start to be able to entangle around 10,000. Then, but if you look at different size scales, you see Rouse dynamics like at the high end of the, and this plot doesn't show the high end, the second crossover, right? Wherever that thing is. I don't think this plot shows it anyway, but where's the modulus? Let's see. Oh, it's the whole thing. Let me just go here. So we have like the plot of log G prime, G double prime, right? And then they cross here. That's where you reach, and this is gamma, log of gamma. That's where 1 over gamma is the entanglement time, right? So then G prime, so it's solid, it's liquid, and then it reaches a fixed thing. That's 1 over ME. That's the G prime, right? Scales with. So that's fixed, and then G double prime goes down, and then it goes back up again, and this guy keeps going, and there's a second crossover. So 1 over that thing is this Rouse time for within the tube. So you have in the tube. So over here, it's actually has enough time. The entanglements don't exist because they relax out. So they're gone. So that you have kind of a choo-choo train thing going. You add more molecular weight, the viscosity goes up linearly. Then all of a sudden, so then it's different here. Then all of a sudden you have another crossover, and again you see the train. I say choo-choo because like in Chinese, train is like chow, something like choo-choo, to remember the word for train in Chinese, but just saying. I don't usually say choo-choo. But anyway, so up here you see the train thing where viscosity is also going to go with molecular weight again when you're at this super high frequency. Like this is beyond human hearing ends here. This is way beyond what you can hear. So you can see the second crossover, and that's where you're talking about the tube. So, and also you can think about this, high frequency is a little teeny bell. This is a giant bell over here. So you're looking at small sizes. So in this plot, you're going from meters, like could be 10 meters, down to like an angstrom. Right, so it's like 15 orders of magnitude in size going across frequency. Unfortunately, it has nothing to do with structure exactly. Right, but basically, if it was a microscope, that would be the best microscope. Would be this oscillatory rheometry thing. So, not sure if that answered it, but we're kind of out of time. But I'm not sure if that answered what you were asking. But it's kind of like you're looking at. It's kind of hard because it's all piled together, right? So it isn't exactly so clear. But basically, the Rouse is really intended to describe oligomers like wax. But here, you have when you talk about when you're within the tube, and they use the Rouse dynamics that they got from wax to talk about the motion of the chains within the tube. Then in order to get reptation, you add that and convolute it with the constraint of the tube and the primitive path. And that gives you the molecular weight to the 3/4 thing, 3.4, right? So yeah, so anyway, there's a lot to it. Like, so we'll go through dynamics a little bit later on, but basically I wanted to, just because the size scales, the small size scales, and these are the features that are there. So you kind of have to mention them here. We can get to it more in detail later, but, all right, so that's it, I guess, but, all right.
Question about A. I missed what you said in the beginning of the class, but basically, me and my teammate were like wondering, like, if we have our thinking right. We thought, like, looking at the C star equation, it looks like the units are completely wrong because
Yeah.
they're grams.
Right, yeah.
So it looks like a unitless.
Right.
Like he's calculating something unitless.
Yeah,
So is that
he
what-
doesn't explain at all what he's doing, right? There is no reference to it.
Not at
It's
all.
just like you have to just figure it
Yeah, he
out.
doesn't plug in
Try to
number.
figure it out, you can't figure it out.
So is that kind of what you want us to talk
Yeah.
about? Just like say, like, we have no idea what he's doing. This is
Exactly,
unitless.
that's, I have no
Okay.
idea what he's doing here.
So,
It doesn't seem to make any sense. It's like, it doesn't even have, I mean, first thing you do is do the units work, and they
right,
don't work, you know? So
yeah.
That's an automatic projection. I would
Okay.
think,
And then do we like, I think my teammate was wondering, like, I guess it's hard to tell, but like, assuming that he just like wrote down the equation wrong and that he actually like did his work correctly or whatever. Like, what would be the units? Would it just be like grams?
Yeah.
Like-
mg per ml is
Okay.
concentration,
Right,
Yeah.
Okay.
You need weight. I mean, it
Right.
could be like, it's gotta be some kind of weight, per some kind of volume.
right.
He's got the volume's there. And he's got a bunch of constants in front of it that aren't really explained. So,
Okay.
yeah, so, yeah,
So, okay, but it is, so you're saying he has the volume?
yeah, the volume's on the bottom of that equation.
Oh, yeah. I
Right,
see what you're
so he's
saying.
got R, I'm looking for R
Yeah,
cubed.
but
and
then on
it's-
the top, he has like a distance cubed as well.
Let's see,
So it's,
so, let's see, where is the C star? So he's got R3D, which isn't,
Right.
that's not defined, okay? He doesn't say what R3D is cubed. Then all these constant, I guess sphere, and then
right,
he's dividing R by 2 for some reason.
yeah, so
Right,
because
so he's
the
got
L
the
over
volume.
L goes away with units, and then the L cubed.
Well, L over L is kind of N, That's kind of like number, that's the molecular weight of the chain.
Okay,
And then L cubed, so that could be okay if you have the density there, the density times the unit cubed would give you mass, and it'll be mass per volume, so it could be, but he hasn't explained it, so you
Right.
can't just say that and like expect it to be right.
all right. Well, we'll just-
How could, all right, the crucial test is this reproducible? Like, can you reproduce what he did?
yeah,
And the
Which is
answer, I think,
exact
is like, no, yeah. So,
okay, all right, yeah, we'll just talk about that then. I just wanted to make sure we were on the right track.
yeah, reproducibility is the main